So here we go. We now have a periodic table that's pretty much complete. You need to know the three different sections, And those sections are the non-metals. Those are yellow. So I'm going to just put on paper, kind of the way I do it with students, things that you need to know. So I'm going to put it on the paper here, and as we go, you'll kind of see what you need to know. I'm going to be very general here. This is going to be those two columns that we have on the left side. We're going to give this a name in the middle right here. And over here, this is our P block, we're going to call it. So this is going to be what I'll circle it in red or highlight it in red. These folks are called the metalloids. You can kind of see them in green there. I don't have a green marker, but they're called the metalloids. Also called semiconductors or semimetals. It's where you get your silicon's in there, arsenic, germanium. They're used for your chip technology because they're not as conductive as metal. They're not as non-conductive as non-metals. They're in between. They're semiconductors, sort of half. Some properties of metals, but not full. So you can use that a lot for electrons going one way, but not another. They're like capacitors. They can allow traffic going one way, but not the other way. So they can be used in your devices. These would be metals, all in blue. To your left, everything excluding hydrogen. Up here, we'll put hydrogen on. It's not a metal. All these are metals. They're all metals. Now we're going to have some different categories for metals within this, but all of this stuff is metals. So we have a lot more metals in our periodic table than anything else. And I didn't put them in a color, but they're yellow. These are called our non-metals. You need this for life. They do, if you want to think of it this way, we're going to get to this later. They do the kumbaya singing, Caleb. They sit around a fire and hold hands. They're not your savages or your, I guess, Black Knight in Monty Python's Holy Grail. They don't lose arms. There's no violence, no electrons being ripped off from someone. They're all just sharing and caring, singing kumbaya and making life. Yeah, you got your life right there. C, O's, N's, H's. Life is good. All right. Know some, I guess, names. This is called a period. We call it a row, but in chemistry, I don't know why we do this. We gave it a little more harder for students to understand what we're saying. This is a period. This is not a column. This is a group. And we can say group 2, group 1, and you're going to learn later, this is not 3, 4, 5, but right here is group 3, 4, 5, 6, 7, 8. And the 8 is our main group elements. Our elements are arranged according to similar properties in vertical columns called groups. And we said periods are horizontal rows. And later on, you'll need to know that 1A through 8A is these first 2 columns and last 6. And they're called the main group elements. So I'm going to put that up on the, I guess, paper here. These 2 right here, plus these 6 right here are called the main group elements. Main group. Can you see that? Did I get that too high or too low? Main group.
Can you flip it so we can see your writing?
Oh, let me see. I'm trying to do the screen and let me see. You're saying you can see my hand, right?
No.
Oh.
We just see your face.
Oh.
We can see your face and like your
There we go.
screen.
Earlier I had asked about it must have gone back to the other one because I thought I'd kept it on. Anyway, thank you, Aaron. Appreciate it. So now can you see my little summary of where we've been?
Yep.
Okay, thank you. So main group, these are called transition metals. These metals in the middle not the ones over here and not the ones over here, but the ones in this part right here. They're called the transition metals. And they really, the reason why they're called that is because they kind of are, sorry, a little, apologize. They're called transition metals because they tend to be a little bit more finicky as their properties go and what charge they have. They're not as predictable in terms of what they'll do or how they'll behave. And there's some cool things, and a lot of our catalysts are in this area, this transition metal zone. All right, so we said main group elements are these columns, first two and the last six. They're called the group 1A, 2A, 3A, whatever. They're also, these are given numbers, but typically if you look at the top of your periodic table, you'll see 7A, 6A, 5A, 4A. Please know, we don't typically see it this way. You might see it both ways sometimes, but if they're going to pick one, they'll often have 1A, 2A, 3A, 4A, 5A. Okay. And we said in the middle, we have the transition metals. Transition metals are that 3 through 12, or this, just that block, that rectangular block from group 2 and group 3 in between. All right. So we've already talked about what's metals, semi-metals or metalloids, and non-metals. And I want to show another video about some really cool properties that they're finding for nanoparticles, because gold, by essence, Aaron, when I say it has a gold color, you think of a particular color tied to gold. Well, we're breaking down that idea, because if you go really, really small with your particle, Stephanie, your little particle of gold, its color starts to change. And let's learn more about that. These guys are kind of nutty. They're from England. 60 symbols. If you want to be really on the nerd crew club, tell me what you saw on 60 symbols and you're in.
Is a transmission electron microscope image. It's formed by having beams of electrons actually transmitted through a sample, and you build up an image from those beams of electrons. And what it is actually is one of these. A single.
Okay, is that gold? Okay, is that the typical gold color? Yes or no, y'all?
No.
Thank you. Someone just, obviously that is not gold. Well, it is gold. Just small pieces of gold that don't look gold. They look purple. So.
Single nanoparticle from this solution of nanoparticles. And the reason I'm showing it to you is because a couple of days ago we had a masterclass for high school students, and the students actually made these nanoparticles. And well, both they and me got very, very excited when we could see the nanoparticles they made with quite simple chemistry. And you can see those right down to the single nanoparticle limit. We take a little droplet of this solution.
Yeah, that's micrometers. That's 10 to the -6. So they're getting down pretty small. And I think this is going to be the nanoparticle here.
We put it onto a grid, and we let the solvent evaporate.
You just jumped to 10 to the 9th, 10 to the -9th. So like 1/1000th of a meter.
And then we put the sample into the microscope, and we can see as you can see, the individual particle. It's a gold nanoparticle. It's a single gold nanoparticle. Tiny, tiny chunk of gold, in this case containing about 125,000 atoms.
This is pretty significant, 125,000. Please kind of remember that as we close the video here. That's a dang small number. You might say, well, no, that's a very big number. In the world of chemistry, 125,000, of course, you wouldn't see it. That's why they had to, I guess, increase the magnification, because they had to see it. That's a small number of atoms. And he's kind of saying there's going to be some, you see the little, beads of the actual atoms itself. Pretty cool.
And we can see the faces on this, we sometimes call it a chunk or a nanoparticle, but it's actually better described in this case as a nanocrystal. You can sort of see these ridges, these edges, and those arise because when you form these particles, they grow out to a certain size and they have certain faces. What I'm showing you here is it's not quite the same crystal structure, but it doesn't really matter as gold has. And you have different faces, and those faces will have different reactivities because if we look at different atoms on these faces, sometimes they're bonded to 3 atoms below. Sometimes in other cases, they're bonded to 2 atoms below. And that leaves what are called dangling bonds sticking out. And those dangling bonds affect the reactivity, affect how the crystal grows. And some faces will grow, some crystal faces will grow faster than others. And we end up with these, you can see these facets on this. So these are facets, and when you grow crystals, you can grow crystals out to very large structures. Of course, if you look at diamonds, you can see the facets in a diamond crystal. But this is at an unimaginably small level. This is 15 nanometers across.
And yet it still has 125,000.
And yet it has 125,000 atoms, yes. When you work, because an atom is incredibly small. A gold atom, diameter of a gold atom is roughly a little bit less than 3 angstroms, so 3/10 of a nanometer. So yeah, we're talking about roughly 125,000. All I've done there, I must admit, before you get your calculators out and all the experts fill up the comments sheet going, how did he manage to work that out? He's out by a factor of 2%. What I've done is I've just taken
I'm going to stop it there, but you get the idea. Gold's not always gold, or making